Buonasera. I'm Piero. I'm Piero Savastano. I come from some years of research in robotics, and then I moved to web development. So I'm trying to mix the things I learned in my years. This is an introduction to machine learning with a special attention on JavaScript. So let's read some definitions. Samuel says that machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. This is really important. Without being explicitly programmed means that we will build a model that learns implicit rules on the data. This is a more formal definition. I hate it. And this one is a more broad one from McCarthy on artificial intelligence, which is the context for machine learning. And artificial intelligence is the science and engineering of making intelligent machines. So now the question is, what is intelligence? So before 1997, playing chess at international level was considered to be human intelligence. After 1997, when an IBM computer won over Kasparov in a world chess tournament, we started to stop considering chess like something that only humans can do in a smart way. So the definition of intelligence is moving through time. Now the researchers talk about general intelligence, which is really difficult for machines, and it's like being able to learn something in a totally abstract way without a definition of the domain of learning. So it's easy to teach a computer how to play chess or how to move a robotic arm or how to do something in a vertical domain, but general intelligence is still really hard. And by the way, the general objective of all of this is to automate, like to let machines do what now humans do. So make our time free from jobs. One of the hot applications right now is computer vision. It's used in security, in robotics, in a lot of ways. The point is, from a video stream, identify objects and try to understand what they are doing. Diagnostics, I'm sorry for the color, and this is used both in clinical applications and in industrial setups, and it's a way to from a wide range of sensors, or when there is something that goes wrong, go back to the main causes of the problem. And it's the same thing like having a person with symptoms, and from a big database of relation between symptoms and illness, we can predict the illness. This is something we see every day, recommendation. It's one of the best commercial applications of machine learning. It consists in giving users suggestions of what can they buy and read or see a video. Coming soon, all this stuff is converging into physical machines, and I give you 3 really good examples. The first one is a Honda robot, humanoid robot, and is able to recognize people in a building and ask them, where do you want to go, and then bring the person in the room. This one is a military robot, and it's built to bring a heavy weight on the field, also in the woods and on ice. It was built by a company that was bought by Google, and their main funding was from DARPA, that is the USA military agency research. And this one is the Google car that I guess you already know. What happens if these machines make a revolution? This is something you can often read on books on, say, people, they talk about this. McAfee told that he's going to start worrying about robot revolution when the day his computer becomes aware of the printer. And I think it's a cool joke, because the main point we must care more now about the social effects of machine learning is which jobs are going to be automated and which jobs are not. And there is this really good book from McAfee, which gives you a simple economic and social overview on this. I think this is really important, because economies are changing because of this. You know, one of the main reasons for unemployment is it's not only bad politics, it's also that machines do a lot of the jobs we used to do. Think about the mail person, il postino, or l'autostrada, il casello dell'autostrada, per esempio. So welcome to the jungle. There are a lot of algorithms. I think there is no person who knows them all. There are really a lot. And I will try to give you the principles behind all of them. The main concept is that you have data, and from data you build a model. The model contains the statistical rules that describe the data, and so you can pose questions to the model and obtain a reply. It's this. We have a lot of data. We use the data to feed an algorithm, and this algorithm is going to build a model by training. So all the data is like the statistical invariances and the rules and the patterns contained in the data are like compacted into the model. And then the user or another application asks questions to the model and gets an answer. So this is the general scheme. This arrow, it's important. So big American multinationals are able to build the really good machine learning algorithms and models like face recognition and text recommendation because they get our data. So it's really important to get the cycle and the economic value of this. I'm going to skip this part anyway. If you want to learn this stuff, you need to get this part of mathematics. I'll go back if something needs it. The main application for the web, we just talked about them. Classification and regression, we already know. Clustering also, and recommendation also. A good example of classification in sentiment analysis. I give you an hashtag, you download all the tweets about an hashtag, and you tell me in which category they correspond, like it's a positive tweet, negative tweet, or neutral tweet. And the same happens with, for example, for documents. Tell me if this news is about politics, is about environment, or is about culture, for example. Regression is more about getting a number from the algorithm. So for example, I give you the perimeter and the position of an house. Tell me how much the house can be valued in money. Clustering, it's, I hope I got the point about clustering. Is there somebody who does not get what clustering is? Can I go on? Recommendation, it's really one of the most famous applications of machine learning. And really, it's understanding what people like and dislike or what they rate more. And at the point you get an user, you want to suggest something to it, and you go over the similar user in order to recommend something that is pertinent for him. And I skipped the mathematical part, but this kind of problems, it's boiled down to every user is like a point in space, in a geometrical space, and you can make recommendation by measuring the distance between points. It's really all boiled down to geometry in this case. There are some issues about the practice of this stuff in a commercial setting. One is about data, and one is about the model. And I use these two sentences to communicate to persons I meet what I mean. So data, you need a lot of data to build models. If you want the model to generalize, you need to have a lot of data. Otherwise, you sample a little portion of reality, and the model cannot extract the statistical rules of the whole. Quality is also important, and it's where the most time is spent in everyday practice, because most of the data you can find it's dirty, or it's full of missing points. So there is a lot of importance in structuring your data, putting it in a database and having it clean. And also pertinency of data. If you want to build a model that will learn to predict what sport a person is doing, you need to gather data about that is pertinent to sport. Like hair color is not pertinent to sport. Choosing an algorithm is not always easy. If you read the research papers and you read the technological press, it's all about new algorithms coming out. But when I see which algorithms are used, they are the same since 20 years. So the one that works are really the old ones. Unless you want to spend a lot, and that is another strategy. Reaching 100% accuracy is nearly to impossible. And I'm quite confident about this. Nobody wants to hear this, and I really insist on this. There is no perfect algorithm. And this is a typical pattern you find when developing a model. In the first few weeks, the first few blocks of work, you can get the algorithm from 0% to 60 or 70% accuracy. But then for bring the algorithm to even 80 or 90%, it's really expensive. That's why also research papers about algorithms, sometimes they publish a paper because they reached a performance that is 2 or 3% more in respect to old papers. So it's really, this is important. Please get this point. And then this is important for JavaScript programmers. There is a collaboration to get into in order to insert the model inside an application that does something on a whole different level. Like machine learning is just one piece in an application, and there are a lot of issues about where to put this model, how to integrate it in your normal stack. It's not always easy. So now let's get into the JavaScript. I hope I took some days to search for JavaScript resources on machine learning, and I expected to find a lot of stuff. In reality, it's still, there is not much yet. So we will try to overview what open source libraries I found, and then build a little model about recommendation. We will get some text and build a model that is able to recommend text starting from one of them. I found these two libraries, Natural and ComNet.js, and also some really good statistical libraries that contains simple machine learning algorithms. And the question mark means that the main point of the presentation is for a JavaScript developer is try to separate as much as possible the process of building a model with an algorithm and with a lot of data, because this can be done on a cluster of computers and it's done in C++, Python, whatever, big data, you name it, and separate these from the actual use of a model. Because the model is sometimes is a little data structure with some little code to run it, and you can bring the model in a website or in an application or wherever really. So it's really important that you work on the integration of the model inside the app, remembering that the model is it's quite small. The model is portable. The training and the data management, it's really a mess. And it's another kind of job. This one is it's pretty interesting. It's a Node.js library that lets you play with textual content. There is a description. Tokenizing means that if you give the library a text, the library is going to segment the text in words, in tokens, in words. This may seem to be easy, like I split by space, but it's not easy because for every language there is an exception on how you do tokenizing. Why you need to tokenize? Because if you get a text and you divide the text in tokens, in words, then you can play with words on a geometrical level. So you can transpose a text in geometry space. Stemming, it's used to simplify the tokens. And an example is, for example, the declinations of the be verb, like I am, you are, I was, etc. I was, I were, I was. Stemming means reconducting all the different forms of a word to the original one. This is good because you want to simplify natural language, which is really complex with a lot of different shades. Classifications, you already know it. Phonetics, it's, yeah, whatever. TF, EDF is really good to measure the importance of a word in a document and in a corpus of document. And it's used to classify, to information retrieval and a lot of other applications. WordNet, it's actually not a library, it's more a database, it's a data set. It's really gold. I suggest you to search for WordNet because it's a dictionary, a graph in which nodes are words and you have connection between the different words. And what WordNet is able to indicate synonyms, hypernyms, eponyms, and a lot of relation with these words. Okay, per esempio, albero, tree. WordNet gives you, is a plant, which kind of plants, of trees there are, and a lot of, there is a little definition and a network of concepts. Why this is good? Because you can start from a text you have, identify the words you have in your text, and ask WordNet which are the related concepts, and then you get a lot of power to make semantic analysis on the text. Then you really start to, you can make the machine actually understand something. ComNet.js is a deep learning library. Deep learning is the new revamped version of neural networks. It's quite complicated to explain here. Maybe another time. I just want to tell you that this is a bio-inspired machine learning. It's about building neurons and layer of neurons and put them together and try to having a little piece of brain resembling a piece of brain, and it's a model trying to abstract data in the same way we saw, but in a more biological oriented way, and it's mostly used in perception, vision or speech recognition and this kind of stuff. One interesting thing to say is about the deep learning is that the biggest researcher in the field, they all abandon academics and they all move to digital bigs. This one is the head of research in Facebook. This one works for Google. This one I think it's the only one still in the academy. And this one is working for Baidu, the Chinese giant. Why this happens, I think this is not happening because they are greedy, but because the big amounts of data you need to teach a deep learning model, it's not owned by academics at all. It's only in big digital companies. So they know what they're doing. They have a lot of money to gather data. They have a lot of quality data. They have thousands of machines, and they have the best talents in the world. And this is something to think about. It's political, sorry. This one, I really recommend this one. It's a statistical libraries, but in the inside you will find a little machine learning algorithms for classification and regression. I think it's good because if you don't know much about these topics, with this library you can get started without being too frightened. And it's easy to read. This is the place to start if you want to learn machine learning with JavaScript, because there is some statistic, and from there you can move on more complex stuff. This one also is good for statistics. There are statistical tests which are good for A/B testing, linear algebra, so working with vectors and multidimensional spaces, vector functions. It's more complicated than the other, but it's also really well done. So the takeaway for a JavaScript programmer is learn the difference between the data and the algorithm and the model, because you will bring the model somewhere. Just don't mind that much about the algorithm and how to teach the model. If you want to learn that, it's better to move to Python or Scala or Python, I would say. But the JavaScript is really excellent because it lets you bring the model nearly everywhere. So there is no language which is so broad-reaching right now like JavaScript. So I think it's a good advantage to know this stuff, the libraries you can use, and how to bring the model in your application. This is something it can be done right now. So now time for the demo. These are the steps we will follow. We will get some data. Then we will choose an algorithm to compress the data inside a model. So we will train a model. And then as an output, we will have a recommendation system. Okay? For text, what we want to do is having a description about the Italian food, and taking one of those descriptions, give it to the system, and the system gives us back similar food, like the one I gave it. So recommendation, similarity. I use this query to get the data. It's a SparkQuell query for somebody knows DBpedia here? Okay, this is also really, it's a little complex to get into this world, but there is really a gold mine for entrepreneurs, because there are you know Wikipedia, there are databases version of the Wikipedia. There are two right now. One is DBpedia that is kept from a German university, and the other one is Wikidata, which is a project of the Wikimedia Foundation. And it's not a simple database or a REST API. It's really a graph with linked data. So you can ask, for example, to this kind of database, like give me the painters in Belgium between 1896 and now, ask really complex questions. And I hope to give a presentation on linked data on another time. I really suggest to look into this. So here I'm saying, give me these variables. I name them. It's like incognitas. Give me this stuff about something, a generic entity, which is food, which is origin in Italy, and give me from this entity the abstract and the label. It's a graph query language. If you use the Neo4j or something like this, it's really similar. And I get a list of ID, like a link to the resource. This is just a Wikipedia page turned into data. So the ID is a link. The food we have, like panzerotti, panzanella, and a description, a short description. How are we going to measure the similarity between this kind of these textual descriptions? With this, the Tanimoto index is one of the simplest ways, and I think it's fairly cool and easy. So I need to measure the difference between two texts, the similarity, sorry, between two texts with a number from 0 to 1. 0, they are completely different. 1, they are completely the same text. And I took these two texts. Okay, JavaScript is a cool language, and be cool and mind your language. What I'm going to do is to take out the so-called stop words, which are two common words, like your, and, be, is, This is common practice because these kind of words can make the data too noisy. So we take out these words to only deal with the important words, the less frequent words, because the less frequent words are the more important in a text, right? Like in every document there is and, so I don't care about and. I'm going to count the common pieces in the text. So cool language, and count them, and I have 2. And then I'm going to count all the words I found in the union of these two texts, which are 1, 2, 3, and 4. I already counted these 2. So it's 2 divided 4, 0.5. The objective is building this data structure. It's a graph. And I'm going to use a node for each text and produce a connection between nodes with the similarity between the text. It's a weighted graph. So the more the two texts are similar, like A text and C text are really similar, so I'm going to put a big weight because they are similar. Otherwise, I put a small one. And I got this kind of table. For example, A respect to B, it's 0.1. They are just a little similar. A respect to C, they are really similar, so I put a 0.8. Okay, can somebody tell me why the diagonal is 1? Ok, perfetto. E poi and then I put this table into JavaScript. There are many ways to do this. And I choose this one, and it's just having an object, which is our graph there and our table there. So for each text, a list of the other text as attributes and the similarity. And this is a good, so the model, as a data, we use a lot of descriptions, right? A lot of text. But the model is just this one with the code that we look into this data structure. And the algorithm we used to train the model was this. Oh, by the way, I wrote it in JavaScript. Sorry, I forgot. This is the similarity index in JavaScript. You know underscore, the library? Yeah, so you get 2 array of strings. You compute the intersection, and then the union, and then you divide the intersection for the union. So brace yourself because a demo is coming. I want to spend some little more minutes on this to get everybody on the point, please. If somebody is a little confused, please tell me now, please. Okay. Where?
Can you explain it again? So what's the formula there?
This one. Okay. These are two sets.
Okay.
Take away the gray words because we don't use them. The intersection is the common elements. Okay, we count how many elements are in the intersection. Cool and language, they appear on both sides, so they are at the intersection of the two sets. And so I get a 2 over the number of unique words I have in both texts.
Okay.
And
so
that is...
the number of the unique words.
Yes, yes.
Okay. So 2 is the common words and 4 is the total number of unique words.
Yes, which is JavaScript, cool, language, and mind.
Yeah, thanks.
And in JavaScript, it's fairly easy, I think. So I take the intersection, how many elements in the intersection, then the union, how many elements in the union. Intersection contain the common elements, union contain the unique elements of the combination of the two sets. And I can, this is, I hope it's clear, this part. Like we just going to build a graph, which is that one. And we will building it by just comparing each text with all the others. And when we need to recommend something, for example, let's say I say to the system, you know, I have a user which is reading text C. Which other text should I suggest to him? Then I'm going to look inside C and search for the highest number. And I'm going to recommend A, because it's the most similar to C we have.
So I know they may be obvious, but from the formula, more words we have in common, and higher will be the number, right? The maximum value we can have is 1 because all the words are in common, and so we have
Yes.
all the words
Yes.
by all the words, so it's 1, and the lower would be 0 or
Yes, yes.
yeah, cool, thanks.
So if the texts are the same, you get 1. Exactly. It's really good. And also, it keeps you safe from different length of texts, because you normalize by the number of unique words. That is the point of dividing, because if you only count the commonalities, then your long text wins. In this way, we give a role. Yeah. Yeah. In machine learning, it's all about normalizing. Really, can you remember about the geometric space and whatever? It's really important if you have, for example, a variable like height of a person, or weight, or age, that you bring all your variables in a range which is common to all variables, like from -1 to 1 or from 0 to 1, because your geometric space must be inside a cube or something. So how are we going to do this? Un po' tosto così. Okay, can you read it? So food.json, I require data is food.json is the data we saw from DBpedia. So it's a list of text about food. I build a new model. I will show you right now the code. So this is my new model, it's empty. And then I train the model, passing it the data. It's what we saw before. So I have the data, I use an algorithm to obtain a model. Inside the model, I have the algorithm we saw. Then here, to verify that what we want to happen, I extract 10 items at random from the data, and then ask the model, give me a reply for this post. So I extract one of the text, and I ask the model, make a recommendation, and I do this for 10 times on random samples. And then later we also give the model a new post. So this is data the model never saw. And I'm going to check if it learned something about food. So let's see a little, so let's see this. New recommender and train. Recommender just brings two objects. I hope you remember the similarity graph we saw before. It's the little JSON. Right now it's empty. We are going to fill it. And bag of words, it's a list of the text I have, but not the text directly, the tokenized version of the text. Like instead of having a text, I have an array of strings contained in the text. So an array of words. So each text is going to be an array of string inside the bag of words. Bag of words is the technical name for this kind of representation of text. When I train the model passing data, I loop over the data and I train the model one by one. What happens here, this is a little more complicated. So the first thing I'm going to do is to tokenize the content. What means tokenize? We saw it. I'm going to take away points, commas, and whatever. I'm going to take away words which are too common because they are too noisy. And then I'm going to, where is? Yeah, split. So the text is going to be split by space, but without the punctuation and without stop words. And I have in output for every text a bag of words, right? Then I insert the bag of words inside my bag of words structure, where I store all my bag of words, each one for each text. And then I put inside the similarity graph this new post, this new text I'm seeing. Now, for each bag of words already existing in my database, I'm going to measure similarity between the current data, the current text bag of words, and all the other ones. And then I'm going to store the similarity inside the similarity graph. Similarity, you saw it. It's the Tanimoto coefficient. This is the algorithm, basically. The algorithm is done by this loop and this function. The model is the little JSON in output. Should I repeat it? Okay. So this happened. I trained the model. So I built a graph, a similarity graph. Now I'm going to check a few texts. Both old, 10 old texts, and one new. So we invent this from scratch. What happens when I run model.test? Okay, model.test. This is one of the texts I have. If I already know this content, if I don't know it, sorry, I'm going to train the model on this new content. So this is a way to refresh the model with each new entering data. Then I take the alternatives I get, which are, can you remember the JSON we saw? It's this one. If you want a recommendation for B, I'm going to extract the alternatives from the similarity graph and give you the highest value alternative, which is the most similar. So explaining code is really difficult. I've never done it. And I return just the, I use this data structure. This is not important. Anyway, I look into the similarity graph and I give away the results ordered by similarity. Let's see what happens. So this is the training part, where the algorithm is comparing each post against all the other ones. I show you again. Each one of the text is compared against all the others. Then let's see the replies. So I asked to the algorithm, give me some recommendation starting from pizza. Like, this is the input for our model. Pizza is a flatbread general, okay. And the model replied. This is the reply. Lasagne with 0.1 similarity, focaccia with 0.09 similarity, and this is the reply. The most matching texts, not a smart one, I say. Spumoni, qualcuno sa che è spumoni? Ok, allora.
No, sono le tipo un gelato pugliese tutto compresso.
Ok, ok. Ah, ecco, infatti ice cream, ok. E lui ha trovato. Il modello ha trovato tartufo, meringhe non l'ha trovato. Gelato napoletano, tortoni, biscotti tortoni, zabbaglione e pignolo. Quindi ecco, diciamo qui non ci ha troppo deluso perché ha trovato il tartufo inteso come gelato, quello al cioccolato. Poi per zuppa all'inglese ha trovato col similarità bassa amaro lucano, no.
Beh, nella zuppa inglese c'è il liquore.
C'è il liquore, ok, quindi qualcosina ha visto. E andiamo avanti perché facciamo una figuraccia qua. Ok, allora questi sono gli anellini, che sono piccoli anelli di una varietà di pasta, e lui ha trovato le penne, i linguettine, gli anelli, le lasagnette e la pastina. Sì, questo torna un po' al discorso di prima, nel senso si vede qui che un po'... Oddio, da quando è che ho cominciato a parlare italiano? So the model, like it is a crap. It's not working that much, but it's built in 2 or 3 hours, and it can do something. So I reached like an acceptable recommendation system in a few hours. To bring this to a good recommendation system, you need a lot of time. For Galliano, which is a liquor, he found Campari, Red Bull, I don't know where Red Bull is between Italian food, balsamic vinegar, and Italian ice. Focaccia, bruschetta, ciabatta. Okay, Napolitan sauce, he found marinara sauce. This is a good match. Lasagne, ciambotta, bruschetta. Sgabeo, whatever. This is a cool one, the recommendation for our new post, the one I wrote from outside the data set. I wrote, we invented a pasta dish with bacon, black pepper, eggs, and cheese, and the model finds carbonara. So it's not that stupid in the end. But then he finds pennetta alla vodka, and maybe there is some work to do. Anyway, this is, 0.22. It's something happened. So now let's try something else. Christmas sweet made of chocolate. I retrained the model, but this is not necessary. The best practice would be to save the object and just load it and use it. This is the point about JavaScript. Like once you have the model, you can bring it everywhere and use it instantaneously. Yes, and this one is good, mostaccioli, you know them? And biscuits, Pandoro. If you want to try something, just tell me. What should I write? Hmm? No idea. Okay, with no idea with olives.
Garlic.
C'è qualcosa che non va? No idea with olives and garlic. Lagane e cicciari, arrabbiata, zuppa, marinara e checca sauce.
Se la puttanesca che dice?
Okay, so I I think there is Nutella. I saw it yesterday. There should be some Nutella around. Nutella. Gianduiotto.
Similarity zero.
Yes. Also the last one, tagliolini with Nutella. What? Infatti lì c'è anche the power of semantic technology. This is really hello world, but the WordNet, it's really good as a data structure, because here we are dealing with text just as a set of words. So the algorithm is not understanding a crap about what the words stay for a meaning. It's just about comparing tokens. But the state-of-the-art recommendation systems are built on semantic technologies. For example, they start from tagliolini with Nutella. They identify tagliolini in a database, semantic database like WordNet or DBpedia or whatever. And from tagliolini, they already know that we are talking about food, about a kind of pasta, where this is produced, where this is going. And so you can explode this text in a graph. And this graph is going to represent one text. And then you compare the graphs. You don't compare the tokens. And that is much deeper.
This WordNet database, how is it done? Is it done automatically, or did people write it manually? Like, how did they make the graph?
The WordNet, you mean? Oh yeah, no, they are, it's like Wikipedia. So they start from a manual effort, and then they produce a data version of this effort. For example, Wikipedia has two different graph database versions, graph data structure versions, DBpedia and Wikidata, and they are derived from voluntary work. So it's the absurd part is that all this data is for free and can be used, and not many people knows it. Academics are really all about semantic stuff, but in this industry, it's still. I hope there is business to be done there, a lot of business, because it really gives you an edge. Of course, you have to invest on it, but gives you an edge. Okay, this was my own one last thing, sorry. Then I go away, I promise. The natural library we saw before. It's this one. And it works in the same way. I have a classifier I add the text to the classifier, but this time I say which category the text appertains. So the first sentence is about software, the second is about software, the third is about hardware. And then I train the model, and the cool part about this library is that you can save the model as a JSON. I was speaking about this before, so you build the model, but the model is going to be really light, and you can put it everywhere. And then you can also bring this model in the client, in the browser. It's really no problem. And then you load the JSON, and you ask questions directly to the model you rebuilt from the JSON. And I think it's interesting to see how this classifier.json is done. So this is the classifier.json. It's just, so software and hardware were our two categories in the text. And it just contains for each of the categories, it just stores the tokens that compare in that category. So even if you have gigabytes and gigabytes of text to feed the classifier, in the end, it will be stored in a hash table with the count of words in the text. So the big this can be is like some kilobytes. And you can really bring it into the client and classify directly in the browser. I think this is really cool for a JavaScript programmer to understand this opportunity. Okay, thank you.